This is Algebra 2 with Trig, Unit 4.2a. We're going to be talking more about inverse functions. What we're going to discuss is the difference between a function and what might just be considered a relation. Let's look back at some yesterday's information. Here we have f of x, so that's our original graph. Here we have a quadratic, which is f of x, and that's our original graph. So which one of these f of x's, that might give it away right there, is a function? And the trick question is, they're both functions. This is a linear function. You can tell it's a function because it passes what we call a vertical line test. If you look at every value of x, do you get only one x value on that function? For any, did I say that right? Any x value, do we get one y answer? Do we get one y answer? And we do. Over here, the same thing. For this parabola, we're just looking at the one that's pointing upwards right now. Kind of ignore the one going sideways. But a vertical line test is only going to touch that parabola one time for any x value. So those are considered functions. Now we're going to look at the inverses. The inverses are down here. This would pass a vertical line test. Any vertical line is going to touch that graph only one time. But look at here. This vertical line touches the graph twice, touches the graph twice. So this is not a function. We would just call this a relation. It's a relationship between the parabola and the inverse. It is not a function. We found where these points would be by switching them and graphing them, reflecting it over the line y equals x. So the inverse is not a function. So we're going to come over here and try to compare these out. Well, there's some quick ways we can do it just by looking quickly at the points. Or we can think about plotting out some of the points. At -2, you'd be at -1. At -1, you'd be up there at 1. At 0, you'd be up at 3. At 1, you'd be at 5. At 2, you'd be at 7. And we get this linear line happening, which is, of course, a function. Now we're going to compare this one. At -1, we're at -2. At 1, we're at -1. At 3, we're at 0. At 5, we're at 1. And at 7, we're at 2. That also would be a function. If you look at every x value is different. We're looking for an x value that repeats itself. It doesn't repeat itself. We're looking over here for x values that repeat itself. It does not repeat itself. That means every x value has a unique y value. So this is a function. Now that might be a little confusing, but let's go ahead and take a look at the next example. We look at this next one. At -2, we're up at 8. At -1, we're down at -1. At 0, we're at 4. At 1, we're down at -1. And at 2, we're up at 8. So that's kind of curving along. That's making a parabola. Look at what's going to happen when we plot out this one. When we're out at 8, we're at -2. At -1, we're at -1. Happens to be on the same point. At -4, we're at 0. At 1, we're at 1. and at 8 we're at 2. So this one is curving sideways. When we look at a vertical line test, it's going to cross that line twice, that parabola twice. Here's the shortcut method. Look for x values that repeat themselves. These repeat themselves, and they got different y's. These happen to repeat themselves, and they have different y's. This is just a relation. This is not a function. Here we have the same x value with two different y answers. The same x value of 8 with two different y values. Here, every x value is different. We didn't have a problem. Let's try this one. At -2, we're down at -6. At -1, we're up at 1. At 0, we're up at 2. At 1, we're up at 3. At 2, we're up at 10. I believe if we looked at this real carefully, I bet it kind of curves through here and then shoots up more. It's not so linear there. Okay, so this is going to be an x cubed type graph. Let's take a look at this one. At -6, we're at -2. At 1, we're at -1. At 2, we're at 0. At 3, we're at 1. And at 10, we're at 2. So it's coming through, curving up, and going that way. These are reflections over y equals x. Vertical line test. It passes. So these are functions of each other. And the quick way to take a look at it, we don't have any repeating x values. There's no same x value, and there's no same x value, so we don't have to worry about any repeating values like we did here. So that's your best way to test it, or you can give it a bit of a sketch to visually see what that would mean. What do you notice? Okay, the inverse of a function is always a function too. Is the inverse sometimes a function, or is the inverse never a function? Well, when we took this linear equation and we did our inverse of it, we switched the x's and the y's like we learned yesterday, we found that to be a function. But when we took the parabola and we flipped it, all the x's and y's, we found out that it was not a function. But when we worked with a cubic, a little harder to tell that this is a cubic, but this is a cubic, and we reflect that. We took these points and we did not see any repeat themselves. So that's a function. So we sometimes get functions, but not always. So how can we look at a table? If the y value repeats then the inverse will not be a function. So what that's talking about is that if we have y values down here that are repeating themselves, the 8 and the 8, the -1 and the -1, they're repeating themselves. The inverse, which is what we get when we come to this side, is not a function. So we just call it a relation. If it's not a function, there's a relationship between them, but it doesn't follow the function aspect, meaning that for every x, you get a single y. Here we have x's with different y's. A vertical line test is a test that we can do on a graph to determine if it is a function. And that's what we've been talking about. We were doing a vertical line test to see if it would cross only once. But here, with the parabola that's on its side, it's going to cross twice. So if we want to think about it, how could we look at the original graph to determine if the inverse is a function? How could we look at a parabola and know that its inverse is not a function? We can't look at a vertical line test to determine the original graph, but if we look at the horizontal line of the original graph, that means when we do our inverse, it's not exactly like this, but it's kind of on its side now, right? Its inverse, which would actually be this one, is not a function. So if we're looking at just the original, we don't do a vertical line test to determine the inverse. We do a horizontal line test. Look to see if any y values repeat in the original graph. We look at the original graph, and there are no y values that are repeating themselves, so the horizontal line test is fine. But when we look at a parabola, the y value is repeated, so that means when we flip it and turn it into the inverse, a vertical line test is not going to pass it. So, a horizontal line test. The inverse of a function is also a function if and only if any horizontal line intersects the graph only once. You will have a function if it crosses only once. This is an example. This graph here, notice how it does that little curve? I suspect that this is an x cubed graph. It doesn't quite act like a linear equation. It definitely does not act like a quadratic. This is a cubic. But a horizontal line, HLT, the horizontal line test, is crossing it only once. This is a test that we do on the original function to decide if the inverse is a function. We don't even see the inverse, so we can't test the inverse, but we see the original, so we can do a horizontal line test to determine if the inverse is a function. So it crosses once, so the inverse is a function. In this case over here, our horizontal line, known as our HLT, crosses twice. So this is not a function. Okay, so we're going to flip our graph over, or paper over, to do some graphs. So we're going to take a look at our equation. This is a linear equation. That should already tell you everything you need to know. If you know it's a linear equation, you should have an idea what to expect. But let's go ahead and graph this. What do you need to do to graph a linear equation? So we're going to start at -3. And we'll do our slope of -2. That means down 2, backwards, or down 2, +1, down 2, +1. A slope of -2 over 1 is a negative slope. It's falling to the right. Or you could look at it the other direction. +2, -1. +2, -1. And continue that pattern all the way to the top of the grid. And we can use our ID to draw in our line, and that is our f of x. So just looking at this function, we don't even see its inverse at the moment. You might be able to visualize it a little bit, but would its inverse be a function? Looking back on the flip side, horizontal line test, the inverse of a function is, the inverse is a function if and only if a horizontal line intersects the graph once. The inverse of the function will be an inverse, or will be a function. So we take a look, and a horizontal line test only crosses a line once. This is the original graph getting crossed once. So it will have an inverse that is a function. So we say yes. Because the original graph passes horizontal line test. So it would not matter where we draw this horizontal line test. HLT, horizontal line test. Any spot we determine to put that horizontal line is only going to cross the graph in one exact spot. Let's go ahead and try to graph this next one. I'd encourage you to pause the video, try to graph it on your own, and then come back and see how you did. So this is an absolute value. We know an absolute value is A, x minus h, the absolute value, plus k. So our h and the k is the vertex. So in this case, our h value is 1 because it's x minus h. This is x minus 1, so h is 1. The k value is 2. This is a positive k. This is a positive 2, so k is 2. So we know our vertex is going to be 1 to the right, 2 up, and we're going to have a slope of 3. So we're going to rise up 3 and go over 1. Rise up 3 and over 1. Then we go the other direction. Positive 3, backwards 1. Positive 3, backwards 1. And that's our f of x function. This is our original graph. Would an inverse of this be a function? If we reflected this over the line y equals x, the graph would open up sideways, and a vertical line would touch it twice. So we don't even have to think about that. We can just look at a horizontal line. And a horizontal line is going to touch the graph 2 times. No, because the f of x, the original graph, fails the horizontal line test. Okay, pause the video, give this guy a try, see if you can graph x cubed plus 1. You'll probably have to plot some points. All right, to try to graph this one, there's a couple of different ways we could think about it. If you know what an x cubed graph looks like, we talked about it a little bit earlier on the flip side. Over here, this is what a x cubed graph actually looks like. It comes up, starts to curve over, and then it shoots up really quick. So that's a cubic graph. We're often used to cubic graphs going up, down, and back up again, and crossing it 3 different times. If it had more parts, like an x squared and an x, it might turn a whole bunch of times. If it was factorable, it would come all the way through and touch at every one of those factors. But let's graph this. So I would typically just go to start at my 1, because I know my x cubed graph is going to go up 1 unit. So instead of being at 0, I'm going to have my new location here at 1. Then I'm going to do my parent function. 0 times 0 times 0 stays right where it's at. If I go over 1, when I plug 1 into my x cubed, 1 times 1 times 1 is 1. I went up 1. If I plug in 2 for my x, 2 times 2 times 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. We can even do that going to the left, but be sure you start from this point right there. -1 times -1 times -1 is -1. -2 times -2 times -2 is -8. And there's your graph. This is an x cubed graph. It just happens to be translated up once. Now we can do a horizontal line test to this. Is there any spot on this graph where the horizontal line test would touch the graph 2 times? Even here in the middle where it's doing some curving, it's only going to touch the graph 1 time. It doesn't curve all the way back down and then curve back up. There's no spot where it's going to touch it twice. So is the inverse a function? We say yes. Because f of x passes the horizontal line test. Okay, let's take a look at a parabola. Okay, you go ahead and try to graph this parabola. Pause the video, you graph it, and come back and see how we did. So to graph a parabola, we could make a table and just plug in points. That would totally work. But I would suggest to start at -1. We know that x squared, we know that the parent function typically is 1 to the right, 1 times 1 is 1. 2 to the right, 2 times 2 is 4. 3 to the right, 3 times 3 is 9. And we'd get the same thing going to the left. So that would be your parabola of a parent function. But this isn't just x squared. This is 2x squared. So that means you're going to go up twice as much. So you're not going to go to the right and up 1. You're going to go up to the right and double that. You're going to go up 2. You're not going to go up 4, but you're going to double that, and you're going to go up 8. And the same thing on the other side. You go up twice as much. And that gives us our f of x. So if we're looking at a parabola, a horizontal line test is going to touch it twice. So that means its inverse is not a function. So is the inverse a function? We get no. Because the f of x fails the horizontal line test. Now this can get a little confusing. What does this x greater than 0 mean?
X is greater than 0.
So we're going to plot the same points. It's the same graph. So we're still starting at -1. We still go 1 to the right. 1 times 1 is 1, but we're doubling that to go 2 up. We're going to go 8 up, like we did here. We could also consider doing it to the other side, but we only want x values that are greater than 0 or equal to. So we're only graphing this portion of the graph. We are not graphing the left side. We're not graphing where x's are less than 0. We're only connecting the points where x is greater than or equal to 0. Now when we do a horizontal line test, because of the domain restriction, this is a domain restriction, we did not graph the entire grid. We only did one side of it, so it would pass a horizontal line test. Would the inverse be a function? And the answer is yes. Because f of x, which is this guy, passes the horizontal line test. F of x had a domain restriction. It didn't take the entire function. It only took the portion that was required in the domain.